Okay, welcome to day 2 of the course on classical recapture, the non-classical negations. So yesterday there was this introduction, lots of grounds that we had to lay down, and maybe a little bit too much. So I took the chance of writing down here some things that you have to know for the exam at the last day. So take pictures, practice, exercise. Just to recall them, if at the top you look at that map called C as the collection of all consecutions, you're going to ask me what all consecutions are. So it depends on what's the kind of sequence you want to manipulate. If you're in set framework, means that you have sets on both sides, then you're going to expect it to contain certain pairs of sets of sentences. If you're in set formula or formula set, meaning that you're looking at assertion-based or denial-based consequence, then it's a little bit different. Doesn't really matter what I want to fix because some people ask me about it, is that the white triangle is a complement of the black triangles. Classical complement. What's not in one of them, it's in the other and vice versa. And also the way of reading these consecutions, when you put a black triangle in the middle of them, it's going to be fixed as, and I've been using this as, say that the simultaneous assertion of all the sentences on the left-hand side is compatible with a denial of all the sentences on the right-hand side. And because the other one is a complement, then it's incompatible, right? And also because some people asked me yesterday about all those symbols, why do I use all those symbols for negations? And it's just a way of us helping to remember that when you have the curly negation, it's probably because they didn't say much about it, just want to put a negation symbol there. And when I write the square negation, it's probably because I wanted to behave classically. And smile, as you know, is power consistent, and a frown is power complete. And the definitions of what it means to be classical, like power consistent and power complete, are over there, in terms of either incompatibility in the first case and compatibility in the other cases. Finally, just to note, the definition of being power consistent doesn't select a single connective. There might be several power consistent negations. You see, it just fails to have a certain consequence property. Many things might fail to have a certain property. And the same for power complete. And just a little note that I presented or mentioned a stronger notion of being power consistent, which is not exploding even partially, and that's the boldly going where no other power consistent logic ever gone. And that's all the logic that I'm going to present here by chance, and I'm not going to prove it, they're all boldly so. Yes?
What's that symbol on the power consistent and power complete lines?
Smile and
To the
frown.
right of the black.
That's the black triangle. It's white, isn't it? It's a field triangle. That's a Q. That's a Q. Oh, you don't like my Q. Bad on you. You're going to lose some points at the end of the final exam.
I was wondering, why don't you express power consistency and power completeness more generally using a set of arbitrary sentences instead of a particular variable?
As I presented yesterday, all the logics that I have here, there will be substitution invariant, and that guarantees that I can use prepositional variables instead of formulas. And just to make sure, when I write a capital Greek letter, it's a set.
Yes, but if you write a set, it could be a formula and it could be also the empty set.
So I would have to define that, and I didn't. So I could, that's another definition, that's not the one I'm using. Okay, I'm just doing the simplest case. Okay, thank you very much. Please interrupt and ask other questions. It's just to remind, this is also from the last talk. As you have seen, it's like we lost our dear consistency and determinateness assumptions, which were present in the ideal standard classical logic. And then we ask ourselves what we can do about it. And there are two basic ideas of trying to recover classical inferences. One of them is trying to find something that plays the role of the lost classical negation. And not going to go over that so much. I'm just going to mention a couple of examples. But idea number 2 is the one we're going to pursue here And the way we're going to pursue this idea is through something we call derivability adjustment theorems. We call, Dieter Patens called it. He invented this name for this. So I stole it unashamedly. Good, so because it does what it's supposed to do, and you're going to see what it looks like in a moment. But the idea about doing adjustments, as you can see here, is adding what might be missing explicitly at the object language level. So if you are able to express that at the object language level, so you should be able just to write down, okay, what if this P behaves well, right? That's your idea of good behavior. All right, so let's see how we can explore this. This is going to be divided in 5 parts today, and I'm going to start by introducing, finally, what is this monster called logic formal inconsistency. Now, as you recall, being para-consistent for a certain symbol, and then you didn't use a smile there because you want to use this as an arbitrary symbol, it means that you, the assertion of a certain formula and its negation is compatible with the denial of some other formula. So there will be, if you want, models which satisfy a formula and its negation while not satisfying some other formula, so non-dadaistic models. I'm going to give this semantic reading later, but it helps, in my experience, to give it now a little bit so that people know that I'm not doing something totally different. But I'll keep reading in terms of assertions and denials whenever possible. What does it mean to be gently explosive with respect to a certain new connective smile inside of a circle? Well, it means that you can somehow, as you see in item 2, recover explosion by adding this extra thing about the smile. But why do I have more things over there? Well, look, the idea is that these 3 formulas together, the 3 sentences together, are jointly incompatible. But what if you didn't need that much? What if 2 of them were already not compatible? So that's why I put the other ones here. Say, okay, no, but 2 of them are compatible. You may assert 2 of them. You just may not assert all of them together. And you might say, well, but this is like collecting 2, these are the 2. Where's the 3rd collection? It's here, right? It's the definition of being para-consistent. So if it's at once para-consistent and also has properties in item 1, it's gonna, it's a lot of noise. Wait, if it's at once para-consistent and respects item 1, then you see that you cannot do the same that you do in item 2 with a proper subset. You need the 3 things together. And you need to know not only that you're asserting P and not P, but also asserting the consistency of P. So that's the role that consistency is going to play. And someone might, I'm going to call it a basic consistency connective, and I'm going to introduce another thing which is not very common in the literature, unfortunately, because I think it should, which is the converse to it, which is saying that if you deny P, then you should assert its consistency. If you deny not P, then you should assert its consistency. Because we intend consistency to be guaranteed only in those situations. Now, this is not guaranteed, but what I had before, that if you have the 2 things, if you have this part and also this part, I'm going to call it a standard consistency connective. Just like the standard connectives that I presented in the last lecture. But it's another sense of standard, so I have to explain a little bit more. But let me just introduce this other connective, which is the black circle instead of the white circle. The black circle is supposed to be the contradictory version of the other one. It's going to be the classical negation of the other one, if you want. And the way that I do it, just like as I do with any classical negation, is by pushing things from one side to the other. So you see that this white ball here was pushed here to the right, and it becomes black. And that's all that I do. It's the whole trick to define the consistency connective. All the things in here are just the same that we had up there by pushing things from one side to the other. So it's supposed to be a sort of non-consistency where this non is quite strong. And also you can define a classical or standard version of it by pushing things again from right to left. Okay? Now, just to make it easier to read, take out the formulas and see what do I mean then by this, all these definitions. Well, you already know being paraconsistent. Being generally explosive basically means that you can consistently assert either or both P and not P, but if you assert them at once, then you are supposed to deny the consistency of P. That's precisely a sign that P is not behaving well. Now, you see that this is an implication if-then. You might want to have the other direction. You might want the denial of P to imply the assertion of both P and not P. And that's what the standard version of the connective does. So now you have if and only if. Okay? And for the inconsistency connective, as I said, the strong intuition is that you should assert the inconsistency of a formula if and only if you are prepared to deny that formula, and the formula here is the consistency of P. So the inconsistency of P is asserted if and only if the consistency is denied. Okay? That's what I said, it's a contradictory version. I'm gonna give you a square for this, right? Obviously at some point. And you all know now what's a square of oppositions. If you did it yesterday, you should. Okay, what is an LFI with respect to a certain consistency connective? It's just gently explosive paraconsistent logic with respect to that connective. As I said, it's an interesting example because if it were not paraconsistent, then it wouldn't have so much of a use as we're going to see. So it's useful precisely when the logic is already missing something. Okay, so in more general terms, what do we expect when somebody says, here is an LFI, we expect this guy to present a non-explosive negation, and now that I know this non-explosive, I'm going to use a smile. You expect also to find a consistency connective. If the guy doesn't present that to you, you have all the right to ask to see it. And a more generous definition would not be just a connective, a unary connective, but could also be a collection of formulas with the same effect. I'm not going to enter very much into that, but the more general definition we had given takes that into account. And the idea is that this connective allows for explosion to be recovered. It sets the behavior of the formula to be just right in terms of consistency. Okay, some other definitions which are common in the literature and we have proposed are a C system based on a certain logic. A lot of people talk about C systems, don't talk in the literature, and they actually referred to specific C systems, which are the CN systems by the Costa, but there is more general definition, which is that it's an LFI in which you can have a unary connective expressing consistency, and it's based on a certain logic. For instance, it might be based on positive classical logic or positive intuitionistic logic by adding to it a negation, which is paraconsistent, and making it into an LFI by adding a consistency connective. And a DC system is even a particular case of that in which not only you're adding this connective, but it was actually already there. It may be defined using other connectives in the language. Now, you might know from the start that it's definable, as it happened in the first cases of this connective in the literature, or you might just find out later on, as you will see in some examples that I'm going to present in this talk. Now, how could one define consistency using other connectives? There are many ways in the literature. These, for instance, you might choose your preferred fetish formula and say that, yeah, consistency is expressed by the negation of that formula, and that is a paraconsistent negation of that formula, like in logic such as C1. And you might say that, well, when you can prove the double negation elimination, or you might have things like these two formulas which are actually equivalent to one thing I wrote yesterday. The classical negation of this thing that people might say it's a contradiction. I don't. Right? The classical negation of that contradiction. And both formulas in the second line are ways of writing that down if the language has a decently behaved conjunction or disjunction, standard ones. In some other logics, you might have, for instance, in a modal logic, define consistency as being if something is the case, then it's necessarily so. And there are many other definitions. I'm not going to occupy you too much with these definitions. I think the problem that really matters is that do these monsters exist? How often are we going to find them? So what are the LFIs and how ubiquitous they are? Questions? Yes.
What if the logic already has a negation? You talked about the positive fragments.
Yeah, that's a very good question. In most examples in the literature, people have started from a logic which was positive in some sense, and then they intended it to have just one extra negation, which would be this part-consistent negation. But this definition doesn't obligate you to do so. You can start by any logic. In that case, you might start with a logic which already has a negation, might even be a classical negation, and add on top of it this para-consistent negation with the counterpart, the consistency connective.
And it doesn't collapse.
No, in general not. In general not. It might. But in general, it doesn't collapse. Questions? Okay, all going fine. You're well motivated as I see it, so I can go to the next slide, which is capturing consistent behavior. You know that I like this thumbs up and down. Let me try to explain what it means for this intuition behind this consistent. Why do we call this good behavior, consistent behavior? So imagine you have something which might be bad or good, like in the circus, right? Kill the Christian. Or not, save him. Now the goal of the classical logician would be that in particular, if something is good, the negation is bad. Now, this is precisely something that you might say, well, if that never happens, then this is not really a legitimate negation, as you have seen in the previous session. So I might want not to force these to be the case, but at least to allow these to happen, which allow for a situation in which a certain sentence is, some sentence is asserted while its negation is denied. Great, so it's not classical yet, but if you keep doing this forever, then you're gonna recover that, right? Now, the para-consistent logician doesn't want you to recover that because he wants you to allow for a situation in which the opposite happens, in which actually you had something good which, when denied, or when putting a negation in front of it, still good. So that you will have models for a formula and its negation. Or, I almost said a pair of contradictory formulas. Wouldn't have a model. Now, this possibility would be guaranteed by writing this. This is a consequence of the definition of being para-consistent. We just put a Q here, and by monotonicity you can take it out. So, and that is expressed by putting this thumbs up over there. Now, one might say, great, where's the consistency connective and what do you expect from it? Well, it's supposed to be this companion to negation, right? And it's going to be until the one slide before the last one, if I ever get to the last one in this session. But the adjusted version that you expect for the explosion would have this format. And what would the consistency, what would the table, the idea for the consistency connective look like? Well, as you say, you cannot assert all this at the same time, and there is a situation in which you seem to be asserting, right? So in that situation, you should put a thumbs down, right? Is what I did here. So the consistency connective should put a thumbs down in that particular situation. It's marking that particular situation as being a badly behaved situation in terms of negation conflicts. Okay, good. What did I do here? I just added the other part. As I said, it's an if and only if it's a standard version of that connective. So in the other cases, I'm allowed to put thumbs up if this is not just a basic version of consistency, but a standard version. Okay. But this gives you a good idea of what kind of truth tables, semantics, or interpretations that you might want to associate to your consistency connective, I hope. Now, if you go even a little bit further and say, great, but this logic actually can prove consistency. I can actually recover the thing that was in under quotes in the first slide, the consistency assumption. What's the consistency assumption? The assumption that you can actually prove the consistency of any formula. Now, if you do that, then you don't have that line anymore. Great, so you're back to classical logic and you have a unary connective that applies to every formula and gives you the truth. Because every formula is consistent there, where the consistency assumptions are present there in classical logic. Okay, so it is there. You thought you didn't have a consistency connective in your logic. You did, because it just turned everything into the truth. That certainly is something you can define inside of your logic if it has a tautology at all. Okay, now, as I said, this means that you're canceling the explosive behavior, and then this smile is actually a square negation if you add all the consistency assumptions back, which we're not going to do because we want to stay inside a logic which is bar consistent. But just in case, if you were to do, that will help us express the so-called derivability adjustment theorem in the nearby slide. Now, one might ask, okay, you want to stay in a place in which not everything behaves consistently. You don't want to add this as a new axiom to your theory. You don't want everything to behave consistently. Great, so how does a logic having that behavior looks like? I'm going to give you some examples, of course, but first of all, I just wanted to present then this first version of the derivability adjustment theorem. It might look complicated, but it's really not. It just says that, well, if this logic is really an LFI, and if you add to it these new axioms saying that everything behaves well, consistently, right? Or otherwise, you might add this one saying that nothing behaves inconsistently, then you might be able to recover, and that's the intention, the behavior that you already had in the classical case. So if you can look here in the middle, have a certain consecution established by a certain consequence related by a certain logic, then you're going to recover it as soon as you know that a certain number of things behave consistently. Now, if you're in classical logic, you don't need to put this because everything behaves consistently. But if you're not, and you want to recover, as you have seen in the case of disjunctive syllogism, the case of contraposition, you want to find a number of things that as soon as you posit, as soon as you agree, as you add the information that it behaves well, that it behaves consistently, then you can do what you did here in the classical case. Classical because you have all the consistency assumptions here. Or otherwise, you might also express this in terms of something that happens on the other side using inconsistency rather than consistency. And actually, this is the original way in which it was expressed by Dirk Battens in the first formulation of this theorem, which was not in the scope of this kind of logics, was in the scope of another kind of logic, which I'm also going to introduce here in one slide. And you're going to see a full course about this in the afternoon. Okay, so I think the question is, what should be our attitude? Just the last click on this slide. We know that we might be able to find a certain set of sentences that as soon as we assume that these sentences behave consistently, then you can recover the reasoning you had before. And what should we do about it? Should we despair? Should we use them to our benefit? Should we assume them to be true? What should we do about it? So the question here is going to be the attitude towards this kind of things and this kind of result. But it's a result that justifies the whole proposal of LFIs in my understanding. Yes, please.
I don't quite understand the result. What is the role being played by the assumption that P is consistent?
Right. So, remember the example of the disjunctive syllogism. You wanted to have this. That's my cue, by the way. You wanted to have this, and then suddenly somebody says, no, but in this logic you don't. This logic you don't. And I say, oh, too bad. Why? Because it fails to have some certain things called consistency assumptions. You say, oh, May I recover it? Yes, there is an adjusted version of it, which looks pretty similar, which is this one. You can do it as soon as you add the information that P behaves well. So here is an example in which delta is the set containing a single thing, which is P. On that version. So this is the consistency of all the formulas in delta. I want to recover this, and now in this LFI, I prove this if and only if I proved it without the assumption in a logic which has it as a theorem. Say, the consistent version of that. Let me put that the way I put there. This LFI with the consistency assumption.
Okay, so
Yes.
I think it was just a matter of reading. So in the middle there, where it says P entails sigma, we are supposed to add as assumption the consistency of the whole delta set, right?
Yes. So this is, when I write this, as usual, when you're applying a function to a set, I'm taking the image of it, right? It's a direct image. It's going to be this in front of it.
Sorry,
Yes.
is this a theory or a definition?
That's a theorem we aim to prove for every logic which is introduced as an LFI.
So it's a definition.
Well, as soon as you prove it, it's a theorem, right? At the moment, it's a goal.
Okay.
Conjecture.
It's a goal.
I mean,
It's not a conjecture because I don't have a logic
I
here
mean,
at
we
all.
would say a logic has
It
durability
should,
adjustment.
if it's an LFI, it should be able to do that.
Okay.
And why should it be able to do that? As I said, these consistency assumptions, they're supposed to filter out the bad models so that you're back to the ones in which they don't exist.
Is this actually true for every LFI or there are?
That's a very delicate question. It should be. It's actually provable for any LFI with a standard version of the connector,
Okay.
which is not the case for all LFIs
Okay.
in the literature.
So
Unfortunately,
when
that
you
was a
put this-
mistake. I'm sorry.
No, no,
My
I mean,
original definition didn't include that. I should have. Because I wanted. I like it.
Okay.
Yes, it's fine. But yeah, it's a goal.
No problem.
You still have to prove it at every single circumstance for logic. Is this clear now with this example? So here the set of consistency assumptions just needs to contain a single thing. And actually it's a subformula of these things in here. If we're so lucky that subformulas will be good, then it's going to be great. But maybe you might have a better result. We're going to talk about some versions of these results, okay? Which has to be proven, as I said, for every single logic. So, other questions? This is really important. Can you see? The slide is over. Yes.
Is there some version of this derivability adjustment theorem in terms of black triangle?
Yeah.
Black triangle.
The black triangle. Good. You can just rewrite everything. This is an if and only if, right? So there is. No one wrote it like that, but there is. Just to replace all the white for the black, still working. Another question? Okay. So I'm not going to enter difficult problems as you see and say, oh, does it work for this very nasty logic? No, I'm gonna give you the simple examples.
Hey,
Yes.
John Marks. My question about the constant well-behaved connective.
Yeah.
About we have a very conditional interpretation of some result about that, or some semantics that take the constant operator as a.
The third session tomorrow is gonna be about semantics. 2/3 of it are gonna be about semantics that we can use to this.
Okay, I just think about that you show.
It's very reasonable. Very reasonable. You should have. You can ask about this in the first day, but you have to wait to the third anyway.
For me, it's more intelligent.
Yeah. understand, but for me, assertions and denials are where the definitions should happen. And one way of making this into interpretations, semantic interpretations, is pretty obvious, by translating this into the truth and the false. But there might be other ways. So tomorrow I'm going to talk about many valued and modal interpretations for this.
Maybe a question of modeling.
Yeah.
Modeling. What's
Yeah.
subject matter of logic?
Sure, sure. I mean,
But it's
open.
open.
It's open, right? I'm presenting consequence relations. They might have very nice interpretations, and maybe through some relatedness approach, so maybe inside some relevance logic. Yeah, it's pretty open.
Okay, thanks.
Okay, so what did the Romans do for us? The Greeks, we know, right? You watched the previous talk. Did a lot. Now, let me give you some illustrations so that you at least believe that these monsters exist. This is one of the most basic examples. That's probably because it's called MP, most basic. No kidding, that's a bad name, I know. It's fixed now. Imagine you start from positive classical logic and you add just what you need to have the dual or the explosion principle inside this logic, which is some version of exclusive middle internalized in the language. And you add just what you need to have something that will look like you're able to adjust your results so that you have explosion back. That's all. That's the whole logic. If you just add these as axioms, you have a logic called NPC, which has some funny behavior. For instance, it is not controllably explosive. I didn't tell you what that is. It doesn't really matter at the moment. I told to the person who asked me yesterday, which is what really matters. You can do better. As I said, you might want to define another logic, which I have worked for many years, which has the converse, which recovers the connective not just as a consistency, a basic consistency connect, but actually a standard version of the connective. Now, there is another name for this in the literature I will never be able to remember, which was given in the book by Carnielli and Cornelio. You probably can tell me the name, MPC, CIW, whatever. I will never remember, so I'll just use MVK. K is for classical, right? Like everybody knows, in sequence calculus, K, right? Okay. I have ideas about using J wrongly for doing the intuitionistic version of it, right? Okay. C1, very famous logic, had to be mentioned. What does it do? Well, it has a standard consistency connective. It also has this funny thing here, saying that the paraconsistent negation of consistency implies P and not P. Be careful with that. And it also has in the second line some very nice stuff in here saying that consistency is contagious. If something behaves consistently, its negation is consistent. If some two things behave consistently, the conjunction of it, the disjunction of it, the implication involved in them, they're all behaving consistently. So it propagates from atomic sentences into complex compound sentences. And here in the logic C1, you have actually the connective defined by way of other things like this funny formula here, people seem to be worried about. Great. You can go further, you can extend this logic. Let me just present this one, you can ask a question of it. It's related to C1. It extends C1 by saying that anything that's compound behaves consistently by default. It's just consistent. Negations are consistent, conjunctions are consistently behaving. So if you have some inconsistent behavior, it must happen at the atomic level. Yes, please.
Sorry, I didn't understand what the last operator, the second line of C1 is.
It's because I put it here. It's just any binary connective. So that I don't have to write it 3 times. I have conjunction, disjunction, and implication. So you write 3 times this. Okay? For any binary connective you have. Actually, in these logics, there are only these 3 binary connectives. It propagates through unary and propagates through binary connectives. So you can imagine that there will be, as I didn't mention here, some versions of the derivability adjustment theorem. So let me go back to them. For instance, in the logic MPK, which was the one that I claimed to allow you to prove the result in a very simple way, you will be able to prove for subformulas. There will be a set of subformulas of the sub-sentences of the sentences involved here, so that if you assume consistency for them, then you can recover classical reasoning. Okay, and in this C1 version, which is the first version in the literature, you can actually improve the result and say that you can take a set of atomic sentences. If you assume consistency of the atomic subformulas of the formulas involved, because of propagation of consistency, then you can take for granted that you have classical reasoning there. So now there are already two proved versions of the derivability adjustment theorem. And for P1, it's even easier, but it's similar to the other case. I'm not going to formulate in every single case. I just wanted to present some other examples. This logic LFI1 was born in the 60s in a work of called Schutte, appeared again in D'Ottaviano and da Costa, proposed with the name J3, was reformulated several times. So what matters is that it does similar things as MBK does, or C1 does here at the beginning. Then it differs a lot. First of all, it adds this double negation elimination and introduction, and it also has some very different forms of propagation of consistency. Very funny things here that you might not have any intuition about, but trust me, that's what it does. Okay, do you have a question, Nicholas? Do you have a question?
Sorry.
It's a lot of noise. I would be happy.
I always look for this
Yes.
test in shooting.
Yes, Big Buttons was the one who pointed out to me that it's in Schutte, and in Schutte it appears with the bottom. The propositional signature is a little bit different, and it keeps changing. The first time that it was proposed with a circle actually was not by us, was by Richard Epstein in his book on translations. Okay, but we reinvented, it doesn't matter. We found it again, and the name stuck, and people keep using this name LFI1 nowadays, but they could use any other name. Doesn't matter, that's what it does. And what's interesting to point out perhaps here is that at least the latter two logics, they have three-valued semantics. So very practical and easy to use. Yes, please.
In LFI1, both introduction and elimination of the negation. But for you said that if you introduce the elimination, the introduction of the negation, the system become classical.
Who said that?
When you s-
I said that? No, I said that for some systems, consistency might be expressed as this formula here. For some other systems, it might be expressed by introduction of double negation. For some other systems, for this system, obviously it doesn't. For this system, actually, you can prove this formula. It's a tautology in LFI1. So it can't be a problem, right? Because you can prove it inside the system. So the problem is actually inconsistency. It doesn't really matter how it's defined, but it's important that you try to find out how each logic does it. And just to point out something else, logic C1 is an example of a DC system in which you can obviously see that inconsistency is defined. And logic P1 is also, you can define inside this logic, but the logic LFI1 is not a DC system, it's a CE system, because you cannot define this connective once you take it out. It must be really there from the beginning, or be definable in terms of all the stuff there in the beginning, as I mentioned in other presentations of this system. Other questions? I'll present other systems. So these are the ones some systems in the Brazilian school have developed, which are examples of logics of formal inconsistency according to these definitions that I proposed. But there is another one that I would like to point out here, which by chance turned out to be also logic of formal inconsistency because it wasn't presented like one from the beginning. That's the Jaśkowski's discursive logic G2, the first power-consistent formal system in the literature introduced in 1948. It's produced by a double translation into the logic, multi-logic S5. And the way that you do these things is that you have to pre-process the connectives from the beginning. Don't really try to understand it, it works. And you put a diamond in front of it to say that, well, somebody said it. So, like somebody's gonna get hurt. If you know this, right? I'm not gonna tell you who, somebody's gonna get hurt. No. and then you define, and there's no set version for the system. Open problem, please work on it. There is a set formula version of the system, which is the original one, in which you just define by way of this translation. Is J is wrong, I have to correct it. Isn't it? It's not slanted, is it? It's wrong, but it should be. All right, what's funny is that then you might find a way, if you're clever enough, to define something that behaves as a classical negation, classic-like negation inside this system, though it wasn't there at the beginning, and use it to define a consistency connective. So it is an LFI, period. Next. Good, so you don't like many valid logics, you like modal logics, you like that I presented an example with S5. Now, pick your preferred modal logic. Now let's do like this. I'm going to use the language of your favorite normal modal logic, which has boxes and diamonds and square negation, classical negation. And I'm just going to introduce the negation of a square as being a smile, the negation of a diamond as being a frown, and then all these funny things here as being 4 unary connectives, which I haven't presented in the other cases, but at least this one you have seen before, and this one you have seen before, and now you see there are also the determinateness version and the undeterminateness version that's going to appear for the LFUs later on. Now, this only uses the basic language of normal modal logic, and what you can prove about it is that it behaves the way you expect, in the sense that smile is a para-consistent negation, the white circle with the smile is a consistency connective, and so on and so forth. So actually, any normal modal logic is an LFI if you adjust it to the right language. We can do better than that. I'm going to show this tomorrow. But at the moment, it's just a way of showing that, as in D2, you might have the structure to express being an LFI inside of a logic, even if it's not there from the beginning. Now, other logics which are well known are not examples of LFIs. Good, because if everything would be, this would be quite trivial as a concept. So this concept leaves some things out, and some interesting logics are left out. That's great. One of these interesting logics left out is the logic C omega, which has nothing to do with the C ends, just by chance appeared together with them. It's not based on classical positive logic, but on intuitionistic positive logic, propositional logic. And it has, it adds these two things in here, over negation, and that's it. This logic cannot define a consistency connected. Yes?
What about the Batten's adaptive logics?
I'm going to talk about, I have a slide about it. Okay, I think it's right after this one. Yes. Very good question. You know what I'm going to talk about. Great. And two other logics that I have to mention here, which are very famous in the literature. The three-valued logic proposed by Asenjo and Priest, called LP. It allows for, it admits dadaistic readings, meaning that you might find a model for all the sentences, which will never happen in an LFI, because as soon as you put the 3 sentences together, you won't have a model for it. And the logic FDE, also quite famous for valued logic, first degree entailment. Dunn-Dunlap logic also can allows you to do that by pushing top as a value for every part. Okay. Good. Now, I mentioned these bridges that might be built in between, very briefly, monotonic and non-monotonic reasoning. So you have a course about this, so I don't have to detail it so much. I just wanted to present, because it's the environment in which it was all first explained. So adaptive logics are a totally alternative way of dealing with these deltas, right? So what should you do about it? Should you look for a way of recovering by finding the things? Well, here, the idea was that why not assume by default that you have it, unless and until people tell you that you don't, or that you have a good reason to believe that you don't. Okay? But that's going to cause some funny behavior. For instance, it's going to fail monotonicity, which is good if you want to do defeasible reasoning, might not be good for other purposes. Let me just very briefly explain what this looks like, because you're going to have a course about it, and I don't have so much time to spend on it. The idea is that you have in my formulation, you're going to see a standard format in the afternoon, which is different. But here you have an upper limit logic and a lower limit logic, and obviously the lower is included inside the upper. And the idea basically in this language is that I'm going to add these connectives here to make it easier for me to recover, to have a derivability adjustment theorem like result at the end. And the upper limit logic is the one which has all the consistency assumptions in the case of inconsistency adaptive logic. So the idea for the derivability adjustment is that whenever you give sentences pi and sigma such that the upper limit logic allows you to infer sigma from pi, you will always find a way of saying that either that happens, or if that happens, then in the lower limit logic, you can prove a similar stuff by adding here what's called a disjunction of abnormalities, as Dirk Bartens is going to explain to you in the afternoon. So this is a result you can prove for any para-consistent logic, a fragment of classical logic, and you might be able to express this in the language by using really disjunctions and negations, but here I'm doing it using the inconsistency connective, just making it closer to what we have been doing. Now, suppose then that the upper limit logic allows you to do it, but the lower limit logic doesn't allow you to produce that inference. The idea, as you're going to see, is that because you can recover this in this case, then you should be able to find a minimal collection of things inside this delta, so that if you put these things, this gamma here, as among your assumptions, and if you put the rest of the formulas at the other side, then you're going to be able to prove this adjusted version of the result. Now, what's the minimal collection and what's the strategy for selecting? Do the course by Dirk Bartens is going to show you there are many ways of doing it. There is the reliability strategy, the minimal abnormality strategy. There are many ways of doing it. It's going to give you different logics depending on what's the lower limit logic and what's the strategy that you choose. But that's a general format in which you might understand it. And what I want you just to focus is on the last line. It might be difficult to read, but what it's saying is that in the lower limit logic, you can actually recover what you had before by adding a number of stuff here on the left, lots of stuff here on the right, but you don't want these to be in your logic. So you want to erase all this. You want to be able to do this in your adaptive logic without having to explicitly write it in there, because you assume by default that all things are consistent, so you don't have to write it down. Okay, so it's a very clever way of trying to recover. And the things that I wrote in here is just to say that, well, if you have these things in separate here, then you may assert them all. If you have these things in separate here, then you may deny them all. But when you put them all together, you may not. Okay, questions? That's the last slide. I don't understand this. Great, ask to the right person in the afternoon. But you see that there is a derivability adjustment theorem at the bottom of it, and that's where it was born. Good. So, yes.
Yeah, a question about the literature.
Yeah.
Literature. If authors use the formalism of if authors use the formalism of S inference related, S compatibility relations, etc.
No, we're going to use from after this course.
Okay. So it's your interpretation, like you are translating into your formula.
Yeah, I'm explaining the best way that I could understand it after having worked on it for a while.
Okay. Thanks.
Okay, so it's a proposal of a way of trying to have some common grounds and common language. But you know that you see that I use this symmetrical version just to make it easier for me also to talk about the par complete case, so that I can more easily push things from one side to the other. Now, okay, this is what I promised now. It's going to be visual, much better perhaps for you to remember. I have already done some of the things yesterday, which I'm going to present here, but maybe they didn't get registered in your mind. They will now, because I'm going to show them again and really insist on it. Now, Remember this? You had the first example of a square of oppositions in my slide using these classical binary connectives, and you had that conjunction is contradictory to NAND, dual to disjunction, and antonym to NOR. Now, what I claim is that you can do much better than that. Instead of taking the full version of the connective, why don't you take just one rule? For instance, think of the rule of conjunction introduction. It's part of the meaning of conjunction. But let's fix this one. If you fix conjunction introduction, you might already ask what's the contradictory version of it, what's the dual of it, and what's the antonym of it. And it's very, very simple. It's that play of pushing things from one side to the other. So when you want to get the contradictory version of it, you get this guy here, you push it to the right. Now it's no longer an and, it's an and. That's it, over. Now, great. We have, for instance, the consistency connective at that corner, and we can produce this corner as the inconsistency connective. We have just started to play. That's a square I did yesterday. I'm going to reconstruct it in front of your bare eyes. Nothing here, nothing there, something here. So, as you remember, I'm not going to try to color things. I'm going to just write this like this. This is the A in there. And I just did this guy here as being the O in that picture. If you don't like all this, you can just think that this is the circle and this is the black circle of the literature end of electronics. Okay, now we're rewriting it, right? We're rewriting the literature right now in front of your eyes. And what we're going to do? Well, we have to know what are the other corners. This doesn't look much of a square, does it? Well, one thing we know, thanks to a question that I had yesterday, is that these two things cannot coincide. Or else you would be able to cut them from one side and the other. You have a trivial logic, right? Because one is on one side and one is on the other side. Now what happens is that we're going to look for the dual of this to put here. And we're going to look for the antonym of this to put here. Or if you don't like it, just produce the dual and then the contradictory, which takes you to the same place. Now, just to finish this square, I have this question of who are E and I. That's why I did all that course yesterday about the S statements, about S consequence and so on. It's going to be so useful now. Now, focus on this corner. This is just the definition of what it means on the positive side of what it means for something to behave like a consistency connective. What's still to be written? Well, this and this. So, the A corner here, if you take all the three A corners here, you have the definition of a basic consistency connective. Great, so what do you do when you do the contradictory? As you know, you push things from one side to the other. If it's black, it becomes white. If it's white, it becomes black, and so on. So this is the definition of the contradictory version of the consistency connective. The consistency connective, which is the inconsistency connective. We already have it here. Great, what about the other ones? Well, what do you do when you dualize something? You look here, what did we do? Everything on the left goes to the right, everything on the right goes to the left, right? Anything left? No, right? So this is looking at one rule, you see that's why disjunction elimination is dual to conjunction introduction. And here, this guy here is going to be dual to this guy here. Of course, down here you have the dual versions of those connectives. What's the dual version? Well, the dual of a smile is a frown. The dual of a consistency connective is undeterminateness connective. Okay, now, going back here. So we already produced some guy over here, which is going to be black, and it's going to be with a frown. Okay? Great. So what about the other one in there? Well, you do the same. If you don't understand what antony means, you can just produce the contradictory version of this by pushing this guy to the other side, or becomes nor, and this guy in here, black, becomes white. Okay, so you have, sorry, something wrong here. This is wrong, right? This should be with a smile. It didn't tell you, but it obviously should be. It's related to that guy. While these are the dual versions. It is black, so it's here on the bottom. Black. And this is. Can you remember that this is supposed to be black and those are supposed to be white? Because I won't be able to do it with a smile and a frown inside. Okay, so this slide makes you not need to remember, but it's not going to stay here forever. That's going to stay. Right, so as you see, if you want the dual version of this, you have something in there. And if you want the antonym version of it, you have this in here. Now, what happens in the top here is that you push things to the left. You represent consistency, you represent determinants, and on the left as assertions you might want to add to your logic. While here at the bottom, you represent inconsistency and undeterminedness as denials that you might want to put on the right. So here, things appear on the left, and here they appear on the right if you're doing the restoration connectives. Okay, now, the definition of the dual of a logical formal inconsistency will look like we're going from here to here. But this just means that we're not dualizing. It means that, it means that we are dualizing. It means that we're not looking at the determinedness connective, but we're looking at the undeterminedness. Okay, this is a big confusion in the literature. It's partly my fault. I have also used a white here instead of black, and okay, that's a bad author. You shouldn't read that guy who did that. The right guy is the one who's in front of you today, and this one's going to use this as I promised to represent these notions, and these are going to appear at the beginning of the next class as reminders for you. But at the moment, this should be good already for you to remember what's going on. And if you want, you can put your AIs, AEIs, and O's so that you have your right mnemonic. Now, why is consistency on this corner? I don't care, it could be anywhere. But in my version of the square, you start in a corner and you produce the others. Okay? I'm going to put it in that corner because I want at the moment. Maybe tomorrow it change. Okay, so just to remind you that if you have a classical negation around, then it's so too easy to do this, as I mentioned yesterday, because the contradictory version means like you are putting a classical negation outside. The dual version means that you're putting outside and inside, and the antonym version means that you're putting a classical negation inside. So you have all these things which are also already present in the ancient literature of internal negations and external negations happening in there. You might not have this classical negation around, so don't use this, don't quote me as saying that you can always do this. You can only do it if classical negation is around. Yes? Somebody raised their hand over there. I was just scratching the ear. All right. Questions? No, sorry, before the questions. It might happen, let me just show you this very funny thing. Remember the squares that might become flat? Well, it might happen, for instance, that these things that we put on the left-hand side of the notion of consequence, they coincide. So you have a single connective expressing at once consistency and determinateness. In that case, if they do coincide, if something is self-antonym, then you're going to have these version of the square. And the contradictory version of a connective is going to coincide with a dual version. Doesn't always happen. It does happen in many interesting logics, yes, but it doesn't always happen. Did I say it enough? Yes, I hope so. Okay, so now that we have all this machinery, I want to introduce formally these other kind of logics which I mentioned before, not the LF5s, but the LFUs. For undeterminateness. So if a logical formal inconsistency has a consistency connective These other logic is going to have a determinateness connective, the LFU, undeterminate. And be careful, it's going to be based on the idea of trying to recover the behavior of negation when negation behaves as being para complete. And it's not dual to consistency, it's antonym to consistency. Okay, passes some authors like myself who might have introduced some disorienting notations at some moment in life. I didn't. Now, the derivability adjustment theorem in this case might be formulated in an extended way, because if your logic not only fails to be consistent, but also fails to be determinate, then you might want to add more than one kind of assumptions here on the left. You want to recover your standard form of reasoning, and you're going to do it by adding a certain number of consistency assumptions and also adding a certain number of determinateness assumptions. Or you can do it on the other side using inconsistency and determinateness. It's basically the same idea for logics which suffer from being not only para-consistent but also para-complete. And if it does happen that these two things coincide, then you have a simpler version of the same result. But it might not happen. Good questions? Yes?
Just for, in that case, L would be both para-consistent and para-complete, right?
Yes, it might be para-consistent with respect to a certain negation and para-complete with respect to another negation. Or they might be the same. When they're the same, then these two things might actually coincide. These two restoration connectives might be just the same.
And in that case, the notion of operator.
Good, I needed a name for it. Thank you very much. Registered grumpy operator.
Could you repeat it?
Grumpy operator. Yes, he didn't finish the question. I'll repeat when he finishes the question.
The smile operator coincides with the notion of the form of the C systems of the Costa, and the grumpy operator will be something like the black operator. The
Yeah.
behavior of the problem.
So in the literature for consistent logic, or LFI at least, the white circle will be the consistency connective, the black circle is going to be the inconsistency connective.
But the grumpy will be the para-completed logic of the Costa, the black form.
Yeah, that's the thing I was talking about. Being black, being white, this is a problem, right? In the world. I'm fixing white to be left and black to be right for the users here.
That's the same notion of
Yeah, left, right, you know. Big problem in the world. Yes, so, yeah, in case you might need all this, you have a single result that includes all of them at once. You might not need it because your logic has only one of these problems, not both, and they might have actually the two problems coinciding, as it happens in some algebraic studies I've been doing nowadays, and very, very often these operators are confused because they're actually the same. They coincide. Okay. Other questions? Yes.
Thinking back to the previous slide, does it make sense to think about outcomes and logic used to consistent based on how big the set triangle is?
Yes.
Or also
Yes, very, very much. And I think the part of the literature which does that really well is the study of adaptive logics, because they really try to find a strategy to see and measure how close you can be. And there are many ways of measuring this closeness. And so there are many associated strategies for finding out which is the optimal set in each case. Okay, I don't have a recipe for this here, but there are some.
Could you repeat the question?
Yes, I could. The question that I just answered was the question whether there is a way of finding an optimal set of consistency assumptions to add. I mean, I reformulated the question, but is there a way of finding this set in such a way that it's going to be really good, optimal in a certain sense, right? That was the question, right? No. You can ask it again, please.
I was asking if we can think of how close something is consistent based on how many elements have to be in that set.
Oh, yes, yes. The question was measuring consistency. Sorry, I didn't answer the right question. So it's is there a way of saying how close the logic is to being consistent by measuring somehow the size of this set of assumptions that I have to add to it? There is some literature also on that. I'm also not going to talk about it, but there are some graded approaches that I have seen in which you try to measure how consistent a logic is by somehow knowing what's the size of this set, or what's the size relative to the maximum expected size of the set. Yeah. So if you have to put basically everything in there, then it's pretty useless, right? But if you can circumscribe the size of the set and find a way of saying that, well, this is almost empty, so you don't actually need to add anything, so it's pretty consistent. And if it contains almost everything you need to add without adding everything, like adding the optimal set that I mentioned before, then it's very close to being very far from consistent. You need to add a lot to guarantee consistency. So there is some literature on this. It's very nice. There's open questions also related to this measure.
Just an observation, there is a paper by John Grant.
Yeah. There was actually a volume organized. Right. John Grant. He organized himself a volume related to measuring inconsistency. There are also some interesting work that has been done here in University of São Paulo on this with Marcelo Finger and Robert Bona on measuring inconsistency. Okay, I might not have the time to talk about this last slide. You tell me, should I give you the last slide or just be open for questions? Because you have so many questions, I probably should stop without the last slide. No questions? You want to see the last slide? Yes, please.
Is there some interesting example?
Martin, could you stand there? Because everybody would like to hear.
I am Martin.
Martin,
Slowly, I will repeat the question. Let him say it, please.
Is there some interesting example of a logic in which you have the four connectives, your four
Yes.
connectives, and they are not interdefinable?
Yeah.
In which you have a negation.
Yes, exactly. I'm going to present it tomorrow.
Right.
Logics without a classical negation in which they're not interdefinable. Yes, there are. Also, there are examples in which you just need one of them and all the others come.
Yes.
I'm going to also talk about them tomorrow. Thank you very much.
Most of the time that will happen, I think.
I'm going to present at least two trends of investigation in which there's no classical negation around, in which, unfortunately, you won't have it. And actually, you might easily imagine this on the algebraic side, also many structures that don't have very naturally a classical negation. You might want to have it. So I'm going to present tomorrow. Some of them actually related to the research we did on evolutive stone algebras. Those don't have a classical negation. Any other questions? I'm afraid of going into this, not having time to finish, or 15 minutes, it might be enough. So, some of you might be thinking that actually consistency is a second-class connective, because it's actually there just to try and restore what has been lost, which negation doesn't have as a property. But look, yeah, from the abstract level, it was defined by way of reference to these other connectives. So there is a smile inside the circle, right? There's a frown inside the circle. But there are interpretations in which actually you can give a meaning to a formula with this connective in front of it without recurring. A meaning, for instance, that's given through many valid and bold interpretations like tomorrow, if you intends to come. So you're going to see it. And great. So the other thing that you might say is that do they stand on their own in the sense that they might have an interpretation which is totally unrelated to smiles and frowns, to negation? Do they make sense in other environments? Well, I claim that they do. There is actually quite a good literature in this white circle added to a logic without a paraconsistent negation. with modal logic, in which this is interpreted as being essence, the notion of essence. Maybe it's the easiest one to understand is the notion of being accidentally true. In the black version of the connective, it means that when you put it in front of a formula, it's true but could have been false. Now, this is obviously a modal connective which deserves being studied, and it will have some properties in common to which ones the connectives that we have here. In particular, it's going to respect the definition of an inconsistency connective. Obviously, cannot refer to a power consistent negation if it's not around, but it will have other properties quite nice. So these already exist. Now, one might ask then if you can give pure abstract definitions of consistency and its neighbors without, in general, without referring to negation. Now that's the task here, and I'm afraid I might do it a bit too fast. Don't worry if you don't get everything that I present here, because I'm introducing a new notion of consequence. Actually, a new notion of compatibility, which is two-dimensional. Before you had the left-hand side and the right-hand side, as you still have over there, and the reading was that things on the left are asserted, things on the right are denied, and I'm changing asserted for two things, two possibly different things in here. Asserted might mean being accepted by a certain agent, for instance, or being entertained by a certain agent that's acceptable, but it also means not reject. Is it the same? It doesn't need to be. If I take acceptance and rejection as being totally independent cognitive attitudes, then non-rejection might not coincide with acceptance. And yet the other side, rejection might not coincide with non-acceptance. Now, then we have something that looks like a generalization of what I presented before. Now the compatibility is in between 4 different things and not 2. Some properties? Well, it's just the same as we saw before, right? You have a version of monotonicity, you have a version of reflexivity, a version of right? And you can do the positive version of it, which is the white triangle. So the one we had before was not the white one, was it? No, it wasn't. So if before I started from this, and then I produce this as the complement. Now I'm starting from this, and I'm producing this. That's the change. So when you see this matrix here, you're looking at something similar to the white triangle, but with more positions, not just 2, 4 positions. Okay, why do I do this? Well, first of all, I'm now basically escaping Tarskian logic, and I can do the reduction as we did before, but it's going to give you not just 2 logical values, but 4 logical values. And if before assertion was misidentified as being true and denial as being false, now you see there's something else happening here. Because actually, being asserted means at once, being true means at once being accepted and non-rejected. Y is for yes and N for no, right? And remember. And being false actually means being at once rejected and not accepted. Being both means that it's at once accepted and rejected, as a lot of you are going to like. And being neither means being at once not accepted and not rejected. So you have 4 logical values behind this new notion of consequence. Why did I do all this? Because it's going to help me. So let me just show you, first of all, that I can express several different notions that we couldn't before. First of all, for instance, imagine that I want to say about this pair of sentences that at least one of them is to be accepted. Well, you might say, what if I want to say at most instead of at least? And what if I want to say that at most of them is going to be rejected, or at least one of them is going to be rejected, or that the rejection of one of them implies the acceptance of the other? They're all different now because acceptance doesn't rhyme with not rejection. And rejection doesn't rhyme with not acceptance. They're all different things. And in this environment, I can capture them all. First of all, look at this white one which is in here. If you look at this diagonal, this looks like we are talking about explosion, right? But explosion not formulated instead of saying that you cannot assert phi and not phi, it's saying that you cannot accept phi and not phi. In fact, the definition of power consistency basically consists in ruling out this reading, that at most one of them is going to be accepted because you might want to accept both. While the definition of power completeness that we saw means that you want at least one of them to be accepted. You want to rule out the situation in which you don't accept either of them. Now that you see that actually you're just against one, you obviously will think, but why is it no one is worried about the others? Why there's so much worried about explosion? What about the other situations? What about the situation in which, instead of having here that anything follows from these two assertions, if you want, you might say that anything, if you deny these two guys here, then everything else is going to be denied too. It's a sort of explosion in terms of denial rather than in terms of assertion, right? But I'm not going to say denial and assertion anymore. I'm going to say rejection and acceptance, just to differentiate from the other situation. But what should be clear here is that we have been approaching the problem from a very biased perspective. We're looking towards only one of the directions. We are considering acceptance as very important in defining power consistency, power completeness, but we're not considering rejection as important in defining anything. So bring your best names to give to the logics that go against one of these two things in here. Help me find new terminology because these things exist. Okay, but if you want to recover a contradictory forming operator, so classic-like operator, you can just add all this. You can add 1 and 3, and you have something that does that, because 1 and 1 says that exactly one of them is going to be accepted, and 3 and 3 say that exactly one of them is going to be rejected, which is what classical logic does about P and not P. Exactly one. Only that classical logicians also assume that rejection is the opposite of acceptance. I'm not assuming that here. Now, if you want instead to have 2, then you have something which is also forming oppositions, but not contradictory oppositions, but antonyms. And that's actually the case for the negation in FDE, first degree entailment. It's an antonym forming operator, as we're going to see tomorrow. Okay, so to deal with this, let me just put more things in here so you see this is what to read. Okay. Remember the problem we have with power consistent logic? We're going to formulate it in this diagonal. Now, what if we want to recover consistency? Well, we have to put the consistency connective here. The 3 guys that cannot be together, right? They cannot be all accepted at once. Now, what about the other things? Well, suppose that you have not a contradictory form in negation because you cannot have it in a power consistent logic, but you have an antonym form in negation like in FDE, for instance. Well, in that case, very simple. You look at this negation in here, cut one with the other, because they're in the diagonal. If you cut one or the other, this P appears here. And this is a pure formulation of the consistency connective without negation. Actually formulated in something that's called Q statement, Q matrices. But you don't need to enter into that to understand. Now, of course, if you go into a standard version of these connectives, you're going to have to add other things, and there are several options. I'm not going to go into them here. I think this is not well understood. Open problems for you guys. Try to help me understand how and which are our options. Which are the things that we can do in order to characterize standard consistency connectives, or in case we have all the kinds of negations around, not having this guy around, for instance, which was useful to write that. Okay? So this is the last thing I wanted to show. Just flash something that's going to appear later on, at least once tomorrow, which is a 2-dimensional notion of consequence that gives you so much expressivity that you might be able to do and to talk about consistency connectives without using the power consistent negation in a pure way, abstract and pure, as we wanted all the things to be, so that we can understand it as some sort of punctuation that's being added in this 2-dimensional environment. Thank you very much. I have a couple questions. First one was yours, this one over here also. Yes.
So, you said classical illusions assume that acceptance is not rejection. I don't. And throughout the lecture, but also yesterday, I think, you've had this attitude of saying, oh, you might not know that this is a possibility, and I'm going to present you this possibility. And that's perfectly fair, of course.
Yeah.
But I assume you also think that this is not just a possibility. This is the right way to go. This is the correct attitude.
You want me to say that? So that it's recorded?
You can say no, of course. But if you do think that,
I love it. Let me say just that I love it. Okay, that's it. I love it.
all right. I was wondering if you could tell us a little bit more as to why you love it, if you do, or why you
Yeah.
don't.
Yeah, first of all, as it's the things I jumped in here. I have these funny characterizations in here. When you write things like this, remember that I said that the principle of non-contradiction was a form of reflexivity, right? When you say that a glut would be the situation in which you are prepared to assert and deny at the same formula. Now, here there are two ways of doing that. You might accept and fail to accept. So you don't want to do that, so you're committed to the principle of non-contradiction towards acceptance. You don't want to get rid of it. Okay, but you might not want to get rid of it with respect to acceptance and still get rid of it with respect to assertion. So if I throw the other thing that I had yesterday away and I don't have the principle of non-contradiction and the principle of excluded middle in the pure formulation that I had yesterday, I don't have anything that resembles a Tarskian logic. I just threw two of the three axioms away. Now, what I show in here is that actually you have a generalized version of it. You have a two-dimensional version of it in which things happen either at one diagonal or at the other diagonal, and you might still throw away your classical assumptions and have logics with real gluts and caps. Does it really make a difference in your life? It might not, because you might look at a certain logic as being given by a collection of matrices and say, well, I want to read this value as being both true and false. You say, okay, great, but is it designated? You say, yes. So it's the true. You might want to read it in a different way, but it's actually the true, because you can do the flattening of the logic. It's actually bivalent. Now, these logics are not. But this was a way of obtaining a framework, a formalism in which I'm not committed to logical bivalence.
It's more expressive. You can
Yeah.
say more things.
You can say more things.
Yes.
Yes. Yes.
And that's desirable.
Yes, there's Alejandro. You.
No, it's also related to the previous question. Is that you're lifting FDE to your meta theory somehow, right?
Yes, yes.
And also it's like, well, I was wondering if you can produce Tableau for your logic using those symbols like signs, right? Those are signs like A and Y.
Yes, yes, and you can use pluses and minuses to do that, but in this environment, you don't need them. The advantage is that you don't need to introduce these foreign labels if you don't want them. But of course, you might want to represent everything using zeros and ones, right? My computer does it. You can do everything with just bits.
But because you can treat them as imprecise values. So, yeah, it's.
Treat them as imprecise values?
Yeah, it's.
Give me more.
Yeah, well, probably I'm not able to elaborate now, but probably later on.
Oh, okay, coffee break. Great.
Yeah, good.
You're not escaping me.
No, sure.
What we have a
Well,
question?
just an observation, why not to call these logics that reject everything Pyrrhonic in honor to cestus empiricus?
No. What is the rejection? You mean
That's representative.
you give me a name to one of these things. If you reject these two things, then you must reject everything else. Is this what you're saying? It could be, but I would like a modular way of giving names to these things, because you see they're growing. If every time you have to pick a new name, people are gonna forget. And my number of things I have to write at the beginning is gonna get
If your names are nice, they stay.
Yeah, I would probably choose something related to conflicts and to ambiguity or incoherence. I would probably go for something that can be adapted and you can use in every corner of this square. Actually, one other question.
Yeah, could you go back a couple slides to the,
Yes.
sorry.
This?
Lógica. Yeah. Or it's about the, yeah, I think it's that.
Here.
You said, could those circles, before you gave the two-dimensional definition, you asked whether those operators could have meaning without the negation.
Yeah.
And so if you have a logic without part-consistent negation and you have those operators, in what sense are those operators the same as the other
Yeah,
ones?
imagine you have a three-valid logic containing some of these connectives, and because you're in a deterministic many-valid logic, you can start playing with your matrices, and you can add new matrices, take some of them out, producing reducts or expansions of the language, and then you tell me, okay, I want to consider this fragment, which doesn't have that connected. I say, great, that's really nice logic. I say, now add this one. I say, oh, be careful in adding. You say, no, it's a conservative extension. Okay, so imagine that you had all the connectives you want, you had the negation, you had the consistency, and I ask you, let's do a reduct, throw away this negation. Say, oh, then we don't have a logic anymore. Of course you have the same matrices as before, just missing one of the operators you had before.
Okay, so
It has the same meaning.
being the same operators would mean being in a logic which can be extended via part-consistent negation.
Yeah, they are interpretable, right? They're still interpretable. They perhaps it's hard to say what they do now,
Yeah.
but it's interpretable and might be useful. And actually, in the literature of modal logic, this has been introduced as the logics of essence and accident.
Okay, so you're saying that when in the literature the people use these operators called accident, essence, etc.,
Yeah.
they are interpretable as consistency and determinants operators in part-consistent logic.
Yeah, they would if the logic would be part consistent. But these logics are not. They are actually fragments of classical logic with the addition of the same interpretation that you would have of these connectives in a logic which would have a part consistent negation. So it doesn't have. It's like you had it at the beginning and you threw it away.
Okay.
These logics are non-normal modal logics. They don't define usually, not always non-normal, but they usually are non-normal modal logics. They don't define boxes or diamonds. They have all the primitives, primitive unary modal connectives. Just like all the logics which are out there. Some of them, for instance, they flatten up this square by having, as I showed yesterday, the contingency and non-contingency operators. Now, I claim that this is actually quite important in philosophy. It has not been used so much. The idea that something is true but could have been false, and that's not the same as could have been true and could have been false, which is contingency. So contingency is not equal to accidentality. So there is some use for this. Yes.
I would like to make an observation for the students and the audience. When we invited João Marcos to deliver this course, the intention was that he could present the LFI logics. But now João Marcos is presenting improved, more generalized and abstract, I would say, theory of the general LFIs. And my observation is that I would like to tell you that the LFI were introduced in the PhD thesis of João Marcos, supervised by Walter Carnielli. And they contain, the LFIs constitute a big class of part-consistent logics that incorporates, that contains many of the known part-consistent logics. For instance, B1, J3, all the CN family excepting the omega, yes, I'm only recalling. And nowadays, today you has showed that some of the adaptive logics also can be interpreted as one kind of LFI.
That's also in the thesis, actually.
Yes. And also,
It's also there. There's a lot in the thesis.
yeah, and so this is a very important class, a very big class of consistent logics. And when introduced, they represented, I think, that like an inflection point in the development of consistent logic in the academic environment. And so, thank you. It's very interesting the form that you introduced and presented the work.
Thank you very much. I guess this is the reason why in the thesis I boldly had a beginning saying prolegomena to any future power consistency. I didn't actually convince everybody, but you see, some years later I went to Australia and I noticed these guys put P, not P, and they put a big ball here. So they had been influenced. Big balls everywhere. Now these other balls here actually, they are also in the thesis, they appear there. The theory I'm presenting here is indeed a little bit more abstract. I promised 3 years ago when I was invited to come to this conference, right, that I would talk about it. And I had, actually I wanted to advertise, I had 2 weeks to work on this at the beginning of this year. So tomorrow there will be something really new. Don't miss it. I'm going to extend this idea, and that's really new, that's not in the thesis, extend this idea of restoration connectives much beyond unary connectives and negations and so on. Anything can be restored as soon as perfection is lost. Don't miss it. Okay, I'm not very good at giving perhaps pointers to the literature, particularly if it's myself, so I try to avoid it altogether, as you have seen. I'm not pointing, but please ask me if you want to find some particular thing in here. If it is already in some paper, I will give you the reference. If it's not, I will send you the papers when it's written. Thank you very much again.